graph of this function. X-axis, y-axis. Now, I want you guys to just panic. Just panic and say something about the graph of this function. Is there any way you can subclassify this function? Please. Thank you.
Parametric.
You don't classify it at all. It's not a function. Well, y is not a function of x, is it?
Parametric.
And maybe I can describe this curve parametrically, whatever that means. Thanks so much, Tyler. But guys, check this out. Maybe this is different. Watch. Can you and I trace this curve with the orientation I got with my arrows? But this time, can you put on some special glasses where you're only one-dimensional? You live only on the x-axis. Let's follow this curve. Watch my fingertip. For this point, I'm going to look at its corresponding x value. Now, as I move along the curve in that direction, watch my fingertip. I move here, then back up, and then go in the other direction again. And I think the movement along the x-axis is a function in time. If I were to project this curve onto the y-axis and trace what's going on with the y variables as points in this curve, I think I'm behaving like this, which is somewhat polynomial. And I think y could be described as a function and time t as well. I'll just think of t as time, and it is a parameter. Not that it has to be time, but it's just a parameter. And so I think I can conveniently think of an arbitrary point on this curve as having an x and y coordinate, where x and y themselves are nothing more than functions. Or sometimes I refer to this point this way: f of t comma y of t. Excuse me, I misspoke. I meant g of t. Where x and y are merely functions in some parameter t. I do not have to restrict my attention to two-dimensional space. Three-dimensional space works fine as well. It's just that when it comes to three space, it might be a little more convenient for you and I to think of the points traced on the curve in three space as the tips of some vectors that are all emanating from the origin. I'll refer to that sometimes as a vector-valued function. You just got to give me 3 more weeks. We'll talk about it. Well, that being the case, let's see if you and I can't come up with some examples of parametric equations. For me to generate the graph of a curve described by these two parametric equations in terms of parameter t, here's something I could do. I hate doing this. In fact, I'm going to really talk fast. This is so crude. I can talk about values of t. Say, for example, 0 to 1/2 to 1 to 3/2 to 2, and talk about the corresponding x and y coordinates. It's kind of clunky, sorry. I'll give you better techniques in a few minutes. If t is 0, I think x is going to be -1. If t is 1/2, I think x is going to be -3/4. If t is equal to 1, x is 0. If t is equal to 3/2, I have no idea what it is. Is it 5/4, I think? And then x is going to be +3. Whereas y ends up changing from 0 to 3. I misspoke, didn't I? Y ranges from 1 to 3/2 to 2 to 5/2 to 3. Now in the Cartesian coordinate system, x-axis, y-axis. Those plot points? So 0, -1 is located which axis? The x-axis or the y-axis?
Neither.
What's that?
Neither.
Yeah, neither. I'm looking at x, y coordinate. I got to come over here. I simply use t to generate these x and y values. I'm really looking at the point -1, +1. There I am. I'm now looking at the point -3/4, +3/2. How about a 0, +2? And then a 5/4, 5/2. And then 3, 3. Oh, you guys, I can't draw very well, but roughly speaking, something like that. I'll put in my orientation. Looks like a piece of parabola. Does it? I made this example up out of thin air. Does it seem like it should be a parabola?
Looks like a root x function shifted.
Yeah.
Can you Easily, can I erase this?
Withdrawing a root X function is drawing the arrow.
I think I can prove better than that. You guys take these two equations, let's just eliminate the parameter. Let me take one of the equations and solve for t. And make that as a substitution in the second equation for t. And I see that x is equal to a t squared minus 1. Check that out. That certainly is quadratic. Well, I should say, x, that's a quadratic equation describing a parabola. I've only got a piece of it because I was restricting my t values.
I have a question that was confusing me on this. So is t the third dimension on the graph, or?
You know, it really isn't. It's more like x and y are functions in terms of this kind of hidden, embedded variable t. I'm not necessarily treating this as some kind of three-dimensional surface. I'm just saying this, x and y change. But they both change as maybe different functions, but in terms of the same independent variable t. So I was not necessarily jumping in higher dimensional space. What about this one? Now, if I were to get an idea of what the heck this graph looks like, to remove the parameter, let's you and I take one of the equations and solve for t. I think t is going to be equal to the inverse sine of x thirds. Now, when I use that value for t, or should I say this expression for t, substitute for t in the second equation, don't I generate this? Where I have to confess t is equal to the inverse sine of x thirds, which means if I were to embed t in a right triangle, to say that it's inverse sine, that it's an angle whose sine is x thirds, simply means the ratio of this side to this side is x to 3, which means, using my Pythagorean theorem, piece of cake. Which means I get to come over here and talk about the cosine of that angle t. But look at my picture. I think the cosine is clearly the ratio of length of side adjacent to t to the length of hypotenuse. Oh, you know what I think it is time for? Cleanup. Does that give me a y over 2 being equal to root stuff? Over 3. And if I square both sides, don't I get this? But doesn't that give me this? I'm running out of room. I don't want to write on the wall. Does that give me an x squared over 9 plus y squared over 4 being equal to 1? What is that?
Circle.
I can't hear you.
Sphere.
I still can't hear you.
Hyperbola?
Oh, it's an ellipse.
It's an ellipse.
Ellipse,
It's an ellipse. Hyperbola, Bradley.
It would be minus, yeah.
Or actually, if you're in three-dimensional space, this is
Ellipse.
x-axis, y-axis. I got an ellipse. Z-axis says nothing about z, so take the ellipse and slide along the z-axis. What do you get?
Ellipse. Cylinder.
How about a cylinder
Cylinder.
going on in both directions? Down.
Wow. So if it doesn't specify, just
Yeah, we'll talk about it another
So
3
it-
weeks.
But it's not a sphere, it's not a circular.
True, it's an elliptical cylinder because its cross-sectional slices perpendicular to the central axis are not circles but ellipses, but it's still a cylinder. Oh,
So a cylinder, but you can, so that, the definition of a cylinder is not necessarily that it's circular, there's not a special.
correct. As a matter of fact, here's one viable definition of a cylinder. In 3 space, it's the collection of parallel lines, which means it doesn't even have to be closed. You guys, do you think that was too much work?
yes.
Yeah, way too much work. Use your math D skills first. Instead, let me just recognize that I've got sines and cosines, and oh, in your deep, deep REM sleep, what's the nicest, cleanest relationship between sines and cosines?
Sine squared of theta plus cosine squared of theta equals 1.
But another name for the cosine of t is y over 2. Another name for the sine of t is x over 3. Oh, did I get those backwards? No, they're right. Oh, wow, look at that. Same answer. So heck,
That's crazy.
so sometimes be more sophisticated before you do a lot of work. I was just trying to impress upon you that if my mind shuts down, I can still remove the parameter in the traditional fashion. Now, I admit, you guys, my first couple examples, they're look at them, they're
Too easy.
Really
yeah, they're
hard.
really easy, aren't they? They're easy because technically speaking, I'm drawing. But I don't have to. I can be more sophisticated, it's just that I have to use technology. For example, again, you guys, I'm just making this up out of thin air. If my computer will answer, if I go into my equation editor and type in some parametric curves, oh, shoot, I can't. That thing's in terms of t. So what do I do? Change the mode. Let me access my mode command. Let me scroll down, and not in function mode, but parametric mode. I'll hit enter. I will dive to my equation editor. And I can type in, you guys, I'm making this up. How about the cosine of 5t? Look at that. When I hit the variable key, it's automatically t because of the parametric mode. And how about being really sophisticated? My y's would be sine, how about 4t? And let me just make sure my windows are correct. You guys don't mind. I just walk in this room. I don't know if they are. How about negative 1.2? Positive 1.2. Even my y guys are negative 1.2 to positive 1.2. Another graph? Ah, shoot, I'm not going to do that by hand. But you can certainly see how the picture makes sense, doesn't it? Because I think with x and y, they're oscillating.
Is it supposed to be all jagged and like
No, I don't have that.
ugly?
You know, good point. Yes, probably it's because of this. My step back from t's is kind of big.
Oh, okay.
That much better, but it's better. I do have limitations with pixels.
Still kind of looks like an Etch-a-Sketch.
Notice how slow it's going, by the way. Because my step size is so low, it's taking a long time to compute these values. A lot of them. But can you guys appreciate how my x and y's, they're actually moving back and forth sinusoidally, just at different periods, that's when getting much more complex curve.
And so this is just that on a.
Well, no, I
Parametric.
chose different equations. This is example number 3.
Where's example number 3?
Example number 3 is how I typed everything in.
Oh, okay.
Fancy.
Oh, it just loves computing. Thank you. Here's my example.
Cosine of 5t, sine of 4t.
When I typed it in Bradley, I intentionally forced the periodicity of those functions to be different.
Okay. That's cool.
Wow. I feel so free and liberated. So much time to just talk.
You say that every class period.
What's that?
You say that every class period. And then
Actually, every class period I say, I come to class, it goes by so fast, I don't say everything I want to say.
You'll change your mind later.
yeah.
Thank you very much.
We have questions.
How about the special one? I've got a circle, and I've just attached a pen to the circle, right here across the origin. Now I want to roll the circle and see how all of this pen marks on the ink board. So we do something like that. Yeah, there's a name for this curve. It's so special,
Cycloid.
we call it a cycloid. And let's talk about moving the circle just a little bit. And let's talk about an arbitrary point on the cycloid. I'll call it P of x comma 1. Let's see if you and I can't, out of thin air, unlike my last silly examples, let's see if we can, out of thin air, generate the parametric representation for the x and y coordinates. So you guys got to humor me with this a little bit. To parameterize, gosh, how am I going to do parameterize? I got an idea. Since the circle started here, I'll allow t to be 0. But that means when I draw a nifty little triangle from the center of my circle, I can allow t to represent this angle. Because if t represents an angle, then when I'm at the beginning position, t really is just 0 radians. Now let's see if you and I can't generate the x and y coordinates at that point. By the way, can I make an assumption? Can I assume the circle has radius of, how about r?
So, you're saying the angle of the triangle you just drew is 0. Is it 0 on the second?
No, I meant to say that if you roll the circle back to its starting position, I think t would be 0 radians. And I confess it'd be a degenerate triangle at that point, but at least it corresponds to t being equal to 0 when I start the experiment. By the way, outside the math class or door, because it's really important how you parameterize your variable. There's not just one way to do it. And maybe there's a way you and I can universalize our parameterization technique. And there is. You will not see it in this book. Well, you won't see it this semester. But here it is. We often want to parameterize in terms of how much distance we traveled on the curve. In other words, parameterize in terms of arc length. That becomes fundamentally important to be consistent in how values on the curve in terms of x and y coordinates are changing. But we're not going to go there. You guys, if you don't mind, I'm going to do this with my blue pen. Oh no. I said with my blue pen. Okay, maybe not. How about with this blue pen? Let's talk about the length of arc. I think the length of arc is the same as this length. Do you guys agree? As the circle rolls, the length of that arc corresponds exactly to the length on the bottom x-axis. Do this for me. We're going to look at the x-coordinate at that point in black. Isn't that going to be this total length? Take away the horizontal leg. Do you guys agree?
Wait, say that
Yeah,
again.
I'll say it again. The x-coordinate at point P located right here. Can I think of that x-coordinate, that x distance, as nothing more than the blue distance minus the length of the horizontal black leg?
I thought the black leg was the removal of the blue part. Okay,
Quite the
continue.
contrary. I think the length of the blue arc is nothing more than this horizontal distance.
Yes.
What's the length of this distance?
Unknown. R theta?
Very nice. It's just r times, you said theta, but you really mean t, don't you?
Yeah, T.
Because I think the length of this arc is nothing more than a product of the central angle measured in radians times the radius of the circle. And so I think it's clearly going to be just nothing more than t times r. So the x-coordinate could be interpreted this way. Goodness. Where r is just a constant, the radius of that circle. However, I need to subtract off, you seem to agree, the length of the horizontal leg. And so I think x ends up being nothing more than r times t minus, well, let's generate the length of the horizontal leg. Use our right triangle definitions. Is it not true that the sine of t is that horizontal leg's length divided by hypotenuse, which is r? And so I think it's the horizontal leg can be interpreted as r times the sine of t. Or shall I say, x is equal to r times t minus sine of t. Do you guys agree?
I have a question.
Yeah.
Well, what is the significance of working in the parametric world instead of the theta world? Because
You know, a lot of times it's a lot easier to deal with the mathematics, given parametric equations describing some curve. Sometimes it's impossible, like my calculus example. There's no way I can represent y as a function of x with that really funky cosine and sine expressions.
okay.
I thought the horizontal leg was cosine.
You know, the way you're thinking back in trigonometry, yes, but notice how t is an angle up there, not over here.
Oh, so
And
it's
so it's the sine of t, which is the opposite over hypotenuse. In my picture, it just happens to be a horizontal leg, but it's really the leg opposite t. And I think to come up with y could be interpreted as nothing more than, let's check it out. Watch. This vertical distance is nothing more than the y coordinate of the center. By the way, it's nothing more than this. Take away the vertical leg of the triangle. But I think using the same logic, the vertical leg can be interpreted as nothing more than r times the cosine of t. Or shall I say, y could be interpreted this way. how I can generate the x and y coordinates as functions of some parameter t, instead of just giving it to you automatically. David?
I lost the meaning of that dotted line.
That was simply what gets spanned out when I roll this wheel, with a pen hooked on it right here.
Oh, I see.
So I just create this image over and over again.
Can you explain how you got y again?
Yeah, I think this y coordinate, this vertical distance, is nothing more than the y coordinate of the center, that's just a radius, minus the vertical height of this vertical leg, which is nothing more than that expression.
So y is, so x is, can you explain how y is t minus sine t instead of 1 minus sine t?
Well, okay, how about if I change colors? How about in green? Take a peek at the center. I think the center of the circle has an x coordinate, which is this, and a y coordinate is that. The x coordinate is RT because that's the length of this blue line segment, which is the same length of this portion of the circle, which is nothing more than an arc subtended by the angle whose measures t radians. And from trigonometry, we easily recognize that as being r times t. Now, I think this x coordinate, this horizontal deviation from the origin, could be interpreted as the x coordinate center, well, there it is, minus the horizontal leg's length. Oh, there it is. And that'll give me the x coordinate at that point that I called x. What's really cool about this curve? This is really slick. Watch. Inverted. And put a little bead on it. That's hollowed out. Actually, do it down here. Actually, I don't care where you put it. No matter where the bead is, if you're just going to let go and neglect friction,
It's like
the
the
amount of
same
time it
amount
takes to
of
get to the
time.
bottom
Yeah.
is the same no matter where I start that little bead.
No.
Yes.
It's true.
It's a really cool curve. It's one of your friends.
You should name him Jack.
So does that mean it travels faster at the top? I don't understand how that would work.
Yeah, it does mean I have to travel initially faster up top because it has to get down to the bottom, the same amount of time it takes for it to get to the bottom when I positioned it lower. Yes, I agree. So everybody, let's talk about slopes and tangent lines. You guys know tricks. I'm talking dy dx. But if I'm given a curve described parametrically, where x is some function in some parameter t, and y is some function, a different function in that parameter t, then I think I can interpret dy dx as the ratio of dy dt to dx dt. So I'm computing that derivative. That's one approach. Who the heck really cares? Well, we do, because I'm really not happy with any one example I've given you so far. Well, with the exception of cycling. I'm unhappy because it's crude, and I think I can do a better job. So, example number 5. Sketch the graph of the curve. By using what I might refer to as an analysis of intervals. You guys, do you mind if I save ourselves some time? I don't want to be really clunky. So I made up an example instead of making it up off the top of my head, just so I don't waste time. I don't remember what it was. How about this one? X equals t cubed minus 3t. And y being equal to a t squared minus 2. When I say use or analysis of intervals, what I really mean is this. Let's compute dx dt. Let's compute dy dt and find their zeros. I think with dx dt it merely gives me a 3t squared minus 3, or shall I say 3 times the product of these two binomials. Man, I didn't know it was going to be that nice. Sorry. I think dy dt is, pretty straightforward. Now, about what values of t is dx dt going to change signs potentially?
0,
I think just negative 1. But dy dt will change signs potentially at t equals 0. I think I have 3 values in t for which I can change directions for those 2 individual derivatives. That being the case, I'll take the real number line and subdivide it into those subintervals separated by those 3 numbers. That's 4 subintervals. So I will talk about my p values as they are to the left of my negative 1 value. I'll talk about t values between negative 1 and 0. I'll talk about t values between 0 and positive 1, and I'll talk about t values to the right of positive 1. Now, because 1, 0 for dx dt is positive 1, what does it say about the graph for the original curve? I know I haven't graphed it yet. What can you say about the graph at t equals 1? Slope of?
0.
Slope of?
So the tangent line.
When dx dt is equal to 0, what can you say about dy dx?
0.
It's undefined, isn't it? And so I think
This is in the denominator.
yeah, I think you get a vertical tangent line when t is equal to 1, or negative 1. But when t is equal to 0, that's when dy dt is equal to 0. And look at this expression for dy dx. If dy dt is equal to 0, what can you say about dy dx? It's 0 as well. So I think t being equal to 0 gives me a point in the curve where the tangent line is horizontal. Just keep that in mind. Matter of fact, if I were to give myself a nice nifty Cartesian coordinate plane, y against x, let's talk about the corresponding points. When t is equal to 0, let's see what x and y are. Plug these in for t, what do I get? I want to generate the points. No, I get a mistake. To find x and y, don't I have to go back there?
Yes.
And I think when t is equal to 0, I get the point 0, negative 2. I said 0, negative 2. This is the point I generate when t is equal to, I've lost it, was it 0?
Yep.
By the way, it's also when dy dt is equal to 0, so that means the tangent line is necessarily going to be horizontal. However, if t is equal to, I don't know, how about negative 1? I think x is going to be, I really don't know, negative 4? Y is negative 1? But when t is equal to positive 1, x is... You guys, did I do my arithmetic correctly? I think I made a mistake.
Yeah.
When t is equal to negative 1, is that a negative 1 plus 3,
Plus
which
3.
is... Sorry, positive 2. Did I get my y coordinate correct? So 2 comma, I said, negative 1?
So yeah, that would be negative.
2 comma negative 1, that occurred when t was this. Sorry, watch my arithmetic. T is equal to positive 1. When I plug 1 in for t here, that gives me an x value of negative 2, a y value is positive, y value is negative 1, so negative 2 comma negative 1. And that happened when t was equal to this. Oh, by the way, when t is 1 or negative 1, I think my dy dx is horribly undefined. I get vertical tangent lines. Well, I have not committed to my analysis of integrals, so let me keep going. Let's go and talk about how x changes with respect to time t. Let's talk about how y changes with respect to time t. Let's do it. Going back to dx dt, it's right here. I think when I'm left to the negative 1, everything's positive. I think when I'm between 0 and negative 1, everything's negative. But to the right of positive 1, I'm certainly positive for values of dx dt.
Any thought process on that?
Yeah, I'm being this lazy. I'm plotting a number line. Plotting these 2 zeros. And ask myself, what are the signs of dx dt over the 3 subintervals? Well, if I plug a billion in for t here and here, isn't everything positive?
Yes.
But when I plug 0 for t, everything's negative.
Yes.
Plugging negative billion in for t makes it positive. That's where I got the positive, negative, and positive signs. I think dy dt is a little easier. Jeepers, t is negative, dy dt is negative. And if t is positive, dy dt is positive. Now, what the heck does it say actually about x and y? I think it says a lot. I think it says the following. Notice how x is changing in positive direction, it's moving from left to right. And then from right to left. And then from right to left. Oh, it changes from left to right. And I think my y values are decreasing, they're going down, down, then up and up. Let's see what this says about the corresponding curve. I think what it says about the corresponding curve, you guys check this out. Over the first interval, I'm moving to the right and downward, I guess I'm moving in this general direction. Over the next interval, I'm moving in this general direction. And then maybe this one, and then finally maybe that one.
Are we, this looks a lot like vectors. Are we implying any kind of vector strategies?
You know, I hate to say that, because I'm using these purple arrows and the black arrows, not really to describe vectors, but just describe the general direction in which the curve is moving.
Okay.
Nothing more. And so everybody trying to put this together, as time goes by, as time is increasing, I think as time goes by, all the way up to a t value of -1, I'm moving in this general direction, up to that point where t is equal to -1, which is right there. And I think moving in this general purple direction means I'm probably doing something like this. Then as t increases from -1 to 0, I move in this direction until I hit the point where t is equal to 0, but that means I'm horizontal because I got a horizontal tangent line there. Next, I do think as t ranges from 0 to 1, that's from this point to this point, I'm moving in this general purple direction, but I better smoothly get a vertical tangent line when t is equal to +1. And here on out, I'm going to move in that general purple direction, probably have some kind of symmetry, maybe passing through that point again. I don't know, I can check. But you guys, isn't it a lot easier for me to sketch a graph this way if I possibly can? I can smoothly see what's going on instead of just merely plotting a silly point here and there for various different values for t. So if I ask you to sketch a curve described parametrically using this analysis of intervals, and this is what I really mean. What do you think?
It seemed like a lot of work.
Do you think so?
Could do another example.
I think it was pretty clear. Try.
So does the sign of dy dx have any meaning here?
Sure. I think the sign of dy dx tells me whether or not the tangent line is positive or negative in this picture. Yeah, I agree completely. As a matter of fact, if t is less than -1, that means before I got to this point, I think dy dx is going to be negative or positive, which is negative. Oh, check this out. For negative values of t left of -1, my slope to tangent lines are all negative. Now check this out. As t ranges from -1 to 0, that means moving from this point right here to this point right here. Notice the ratio of dy dt to dx dt is going to be positive. And look between my two fingers. Any point in the curve has a positive slope. Not looking at direction or orientation anymore, because we're just talking about dy dx. And I think I'm consistent here. That was a big question.
So how does that correlate between 0 and 1?
What do you mean?
Because you said that from,
Oh, you mean from t range from 0 to 1?
yeah.
Let's see if this makes sense.
Okay.
If everything's here correct, then dy dx is this divided by this,
Yeah.
which is a positive divided by negative, which is negative.
Yes.
And so from t being equal to 0, that's this point,
Yeah.
to t being equal to 1 this point, I think slopes and tangent lines should all be negative, and look at that, they are.
Oh, tangent line.
And again, we're talking about dy dx, we're no longer looking at the orientation of how I traced out this curve.
Gotcha.
So I still think it jogs.
So you're just looking at in between t and like -1 and t. If the x coordinates are increasing, or if x is increasing between that value.
I'm so sorry, I'm just kind of tired.
'Cause it's
I
moving to
lost
the
track. I
right,
apologize.
so-
Can you repeat that?
Well, I'm just looking at your arrows for x and y there.
Yes, yes.
And does that just mean that the x values are increasing to the right in
Yes.
between those bounds, and the y values are decreasing?
As t ranges over this region.
Okay.
Yes, that's exactly what it means. And then in purple, I just put those two movements together.
So those xy's are
Okay.
the original functions.
You know what, Linda, I never looked over there. These errors simply came from these signs.
Okay, I see.
The only time I actually look at the original parametric equations was number 1, when I differentiated. Number 2, when I wanted to actually plot those points
Okay,
specifically.
so that's what you're saying. And then, what do you call it?
There's nothing wrong with referring to as critical points, just think of these two as critical points for the x function in t.
Okay.
And those are the critical numbers, not points, critical numbers for this function of y.
So be critical numbers, you would call those.
You know what? You just reminded me of something. I think your author back in Math 30 might have referred to them as critical points. I think he did. That is by far not a phrase you want to use.
Okay.
Critical points are something completely
Because that's
different.
something, because this is parametric equations versus just
Math 30.
correct. So
Yeah,
I
but
think
even
they
Math-
had a special name.
Even in Math 30, I think he misnames those values of x. He called them critical points. He really meant critical numbers.
Okay.
I got a whole different way I'm going to use the phrase critical points in Math 32. So I need to reserve those phrases.
So, is this graph the graph of the original or the graph of the derivative?
Yes, I think what you finally see in this picture over here, although it doesn't look very nice, I'm sorry, really is nothing more than a graph of the original curve described by those parametric equations.
So, in order to get where the line intercepts itself, we would solve for, we would make x and y equal to each other? I mean, or
No, you guys, I know we need a break, but that is such a good question. It seems like this curve crosses itself on the y-axis, doesn't it? Let's see if that's true. Because I'm serious, I might have made a mistake. So to find the y-intercept, I'm simply going to find when x is equal to 0. To find when x is equal to 0, let me plug 0 for x. I get this. I get this. So when t is equal to one of these three numbers, I cross the y-axis. Now, I think the x-coordinate is going to be 0 in each one of these three cases. But let's see what the corresponding y-coordinates are. I might end up with 3 different y-coordinates, which means I have 3, not 2, y-intercepts. I might have made a mistake. Let's check it. With my y equation, when I plug 0 for t, I see that y is equal to -2. But when t is equal to plus, or for that matter, minus root 3, notice that y ends up being 3 minus 2, which is 1. And so I think for 2 t values that gave me a next value 0, I got the same darn y value. I was right with my suspicion that there is symmetry. I really did cross myself when t was equal to 1. Well, when t was equal to root 3 or negative root 3. I just passed through the point 0, 1 for those different values of t. So I was right. Yeah, Sean?
So when we get like something like that where we're filling in a lot of the crossing and things ourselves, do we need to specify what those points are?
Yeah, I think I should.
Your 4 ranges for T right there that you started with, are those, will those be the same for all of everything, or?
Quite the contrary. It all depends on what happens when I set dx dt in factored form. So I need to take my dx dt and factor it to find those critical numbers for the x function. And I just happen to generate 1 and -1 in this example, but they might not be. They could be a variety of different